Okay, so let's begin. So I'm starting with the project that I built in the previous video. So if you haven't watched the previous video, you should come back and build this project by yourself. And you'll see how to make this kind of small automation where you can create the geometry and the mesh parametrically. If you just want to know how to simulate using Aster and how to add it into YACS to have a full automation, then you can just watch this video as well. The content I will show you will be kind of independent of what I've shown before. I'll just start from the model generated here, but if you have any MET file available, you can just directly use it. So just to explain what I'm going to do, first I will set up a Aster study into the Aster study module using this mesh model. So I'll do a very simple analysis in which I'll fix one edge and I will apply a pressure on the other side. And when I will have this one, it will allow me to obtain the different files I will need to generate a node which will run Aster basically. Now the kind of tricky part is that if you watch the previous video, you know that what I did basically to do that is that I exported the trace of the Python file and I just basically pasted it here. So every function, everything is already done for me. Unfortunately, this doesn't work with Aster and Aster Study because simply the Aster module is not fully compatible yet with Python. So, I'll have to use another method that I'll talk about. So let's start first by creating the Aster Study simulation. And when I will have all of that, I will show you how to integrate this into a node. Okay, so the first step will be to add a new stage and then read my mesh. Then I will take one of the mesh that I have already available. Let's, okay. Now next step is to assign a model. So that will be finite element model, which will be everywhere, mechanic, modelization 3D. Okay. Then let's create some material. So define a material. So my material elastic, linear, isotropic. So I can, well, I can just call it matter, or I can call it steel if I want. So that's where I have to be careful with the unit. For the dimension, I use 500, 500, and 4, if you remember. So those are millimeter unit. So I have to enter the Young's modulus in MPa, not in PA. So the value I will use is 197,000 MPa. Poisson ratio will be 0.3. Okay. And let's assign this material to my model. So let's create a model here. And let's assign that everywhere. And the material that I just created. So that's my field, material field. Now let's create the loads. Assign mechanical loads. Let's fix some degrees of freedom. So I'm going voluntarily fast because it's not really a tutorial about how to use Aster here. You should watch my other videos if that's what you want to see. It's just to show you how to build this case for this specific study. So let's choose one of the element groups that I created on this model. So let's apply let's fix the degrees of freedom on the X minimum face here. You can check on the model that this is the correct face selected. So now let's fix degrees of freedom. So I want basically to fix all the 3 degrees of freedom. So I could just like that do this because this is 3D element, so I only have to fix the translations. Or I could also just select this liaison encastrée. That's the same, it means basically that everything will be fixed. Okay. Now let's find out the pressure load. So I will search in the box like that, press and press rep. So press pressure distribution. This is the type of load I want to apply to the other face. I will select a group of elements X max this time. So on the other side of the plate. And I will give it a value of minus, let's say 200 MPa. So we'll see afterwards in the result if this value is reasonable, if it doesn't deform too much because I'm still in small deformation. Okay, and my loads are now created. So I'm ready to create my simulation. So my simulation will be static mechanical analysis. So let's choose the material field. Let's choose the model. Let's add the load. And that's all I need. Now, I don't really need that for this analysis, but I'll still add the calc champ to get the stress as well. Who knows, maybe I'll want to post-process the stress later on. So it's good to calculate that as well. So let's say I want found me this stresses here. So I'll use sec alga, sec elno, and sec ne. Okay. And this should be the same name as the study, or I can check this, reuse the input object. So this will automatically give it the same name. And now I need to print the results. So set the output results to so I create several files. I'll create a file called I don't know, plate res.rmed. This will be a MED format that I can use to open using Paravis and look at the results. And don't forget to add these results here, otherwise you'll get nothing into this. And just check this. So all the results will be exported to the file. And now I'll do something in addition to that, because I would like to have also the results as a text output. So I can use some Python to extract the information later on. So I'll add a second output result. So I'll get result output into both the MED file and both text file. And let's call this one, I don't know, let's call that plate res plate res.txt. Now, if I want the text format, I have to select results as the format. Okay, it automatically deleted what I had here, so I have to recreate that. Okay, and this time I will add again results. And I don't want all the result into the text file because it's a bit too much and the text will be too long. So I can use the option here to actually filter the results that I will get. So for that, I want to output only, let's say, the displacement. So I can choose depth, like the déplacement, so it means displacement. And I want to output the maximum and the minimum value of all displacement into a text. Okay. And now the simulation is complete, so I can run the simulation to see what happens. So for that, let's go into history view. Let's click on the stage and let's run that. Okay, I should save the study. Run. So simulation is now complete, so we can have a look at those results and see if they are correct. So go to the RMed. So you see that I have two files generated, RMed and text. I can, let's say, open and editor this text file, and we see that it basically contains the displacement and the minimum value and the maximum value of the three components of the displacement at one node here. So at several nodes, but this is the maximum value, right? So it tells me which node gives the maximum value. And so the displacement maximum value is 0.5 millimeter. So I think regarding the thickness is 500. So I think it's reasonable for small displacement. Okay, so now that the model is set up, I got my simulation ready and all. Let's have a thinking about how to actually automate this and how to put that into my YACS scheme. So for that, let's come back and look at my result files. So this is my folder in which I have all the results. Again, I'm using Ubuntu because this, what I will show you here, will only work on Ubuntu version. I think, because the Windows version has different executable for the Aster as run. So this probably will not work on Windows, but you're welcome to try and let me know if it works. I'll show you on Ubuntu. And so these are the files that I'm getting. So you see I have the result, I have the text file, and I have this study file. So this is automatically generated by my Aster study. And in this here, you have the run case. So open that. And you inside that, you see that you have several files. So you have the com file and you have the export file, and you have also an exported object which contains the mesh. So if I open this, you see that this basically contains all the comments that I defined. And but how does the com file knows about the mesh and the other files? Well, it knows about it through a system of units, and basically these have to be defined into the export file. So if you look at the export file, this you have a certain number of so up to here, those are basically some statistics, some parameters for the solver. So how long it should run, how much memory it will require, which kind of Aster version it needs, all that. And then you have definition of the different files which are corresponding to this project. So you see, because there is a small f at the beginning of the line, which means file. So you can use like that com file, and the input file have a D here, and the result file have an R, and you have some units. So the conf file is the most important, so it is the unit number 1. Then you have the met file, which is the object, which has unit 20. You have the RMed result, and you have the result text file, and the message test file is basically the log from the solver. So this is the export and all this. This is pretty important. But now the question you should be asking yourself is, how do I run that without Salome? And how do I use Python to actually run this export file? Well, the answer to this question is through a certain functionality of Python, which so I'll give you the code. So it's a pretty short code like this, and it's using a function of Python called subprocessing. So if you want to run code Aster without the graphical interface, you have to run an executable called asrun, and this executable is basically the command line version of the GUI Aster executable. So if you give the export file to this asrun, it will be able to process the study. So now this asrun is a Linux executable. So I can have a look where it is actually. So if you have a look at the Salome Mecha binary, so let's have a look at my path, for example. So let's say I'm going to home, Salome, let's find where my Salome is. Salome Mecha, then you have an app v2 public, which contains a tool folder, and you have basically several versions of Code Aster. So this is the front end version that is used into Aster study. Then you have a bin, which contains all the binaries. And this, you see you have asrun, which is basically used to launch. So my asrun is inside this folder. And what I need to do is to first to construct a path to this folder, and then to give it to a function of Python called subprocessing. And subprocessing is basically, let's say, it's a Python way to run terminal executables in Linux. So it's pretty useful, and it is a way to basically put into a black box any kind of Linux executable and run it using Python code. So it's very, very useful to know how to use correctly the subprocess. So I will not go into all those details here because it's a bit complicated and you need to have a bit of Python knowledge. So the only thing you will need is to take all of that, and we will copy that and paste it into a new node here. So let's create a new Python node. So this will be inline script node. This will be my Aster node. And I'll paste the code here and click and apply. And don't forget to link that to here. Now, the kind of tricky thing is to choose the right path for your files. So make sure that you're, sorry, I'm on the wrong node. I'm sure that you are into the right folder. So if you see here my, I'm into home, Cyprien desktop plate. So I'm not into the right folder and I'm not giving it the right export file. So I have to go to this path. So let's basically Control A, Control C to copy that. And let's paste that here. And we see that the file is just called export here. It's not even called something.export, it's just export. My executable is at this path, so this should be correct. apply. And now I'm ready to try and hope that this works. So let's create an executable scheme. And let's try to run that. So now it's start. You see the node is blue here. It means that it's running right now. Something is happening. So code Aster is running. Well, I hope. And we'll see in a few seconds if the study is successful. So it's became green, everything is cooled down, but that doesn't mean that it works. It just means that the code has been executed and it's finished, because this Python doesn't have any feedback on is my Aster study actually successful. So how do you know if it's successful? Well, you go into the scheme like that and you click on the container and you go up to the end. And now you just go down and look at this. And I think it was successful because I have the code exit 0, which basically tells me that everything was executed without any problem. So that's a good sign. And we see that I have now some results which appeared here. So let's open quickly the results file in Paravis just to have a look at the result and make sure this is okay. So you see this is what I get. I get a plate with the deformation in the right direction and the right amplitude as well. I can look at the mesh as well, so one layer of my grid meshing, so it's fine. And let's look at the nodal stress as well, which look good. So everything is fine. My code Aster simulation was successful. So as this is done, we are okay for this video. And now maybe we can have a quick discussion about how would you make that parametric, because you see I showed you some way to insert some parameters here and to change in function of those parameters. What if I want to put some parameters for the simulation as well? Well, that would be a bit more complex, but it's doable as well. The only thing you need to know is that to modify the simulation, you need basically to rewrite the COM file. So you could think about adding a node, like another Python script node, with the sole purpose to rewrite the COM file, and you could give it input certain values so he would rewrite the COM file in function of those values, and then feed that to the node Aster. So instead, this node would run the COM file writer first, and then it will launch the Aster study, and that way you could make it parametric. I will not do that in this video. This will be a small exercise for you to see if what I've done previously worked for you, and if you are able to solve this kind of small problem. And if you really cannot do it, well, please leave a comment in this video, and I'll explain maybe how to do it, or on the blog. And in the next video, we'll talk about post-processing, because right now I'm just outputting the results. Now, probably what you want to do is how do we link that to Paravis, or how do we link that to some kind of result post-processing that will actually put that into an Excel file, or doing some interesting stuff with it. And we'll see that in another video. So I hope this was useful. Thank you very much for watching. If you like the video, please give it a thumb up. And let me know if you have any questions in the comments. Thank you very much.